as I told you, heterogeneous computing, you have the host and you have the device. Okay, host is the CPU and the memory. It's called as a host. So in your desktop computer, your CPU and memory, whatever will execute is the host part, and the device part is the GPU and the CUDA card. So whatever is executed by the CPU and the memory, that is the host part, and whatever is executed by the device, that is GPU and its memory, is the device part. So that is called as device memory, the memory in the CUDA card, that is GPU, and the memory of the desktop is called as host memory. Okay. So as I told you, in heterogeneous computing, whatever is the part that CPU and the CPU memory will execute is the serial code in the main, let's say. So it will be executed sequentially. Whereas whatever is executed in the parallel part, kernel function, is executed on the GPU card or the CUDA card, and that will be executed parallelly. Okay. So in the heterogeneous computing of CUDA program using C++, there will be sequential execution, parallel execution, and maybe again sequential execution. So depending on the way the program has been written, it will contain sequential execution also and parallel execution also. Okay. So are you getting what is the concept of CUDA programming initially at least? So you have a computer which is made up of the host CPU and the host memory, that is called as the host part of the computer, and you have the GPU card or the CUDA card, which is called as the device. Okay. So program will basically execute on the CPU also, and some part will execute on the GPU also. Whatever is executed by the CPU is a sequential part of the execution. Whatever is executed on the CUDA card is the parallelism that will be exploited from the CUDA card or the GPU. Okay. Yes, getting this concept that there will be a host memory and a device memory. Yes. So basically what you will have to require is that you require a desktop PC, and to that the CUDA card will be attached. That will be the requirement for CUDA programming. So the CPU and the CPU memory is the host part, and the CUDA card and its memory is the device and the device memory. Okay. So simple processing flow. So you have the CPU memory, and there is a bridge between that, the bus of that. Okay. Then internal bus particularly. Okay. Then you have the giga thread part of the GPU. It will have its own parallelism part involved in it. We'll go into it later. Okay. And it will have its DRAM. This is part of the device memory. Okay. So what will happen initially is that copy input data from CPU memory into GPU memory. So first what you have to do is that you have to copy input data from CPU memory into GPU memory. So we'll see how to do that. There are APIs available for doing that. Okay. Copy from CPU memory to GPU memory. Okay. Then load GPU program and execute caching data on chip for performance. So GPU part of the program is loaded into the GPU card using caching data for better performance. Okay. And GPU card will execute the parallel processing related code in your CUDA program. So first you have to copy the input data from CPU memory to GPU memory. Then you have to copy the part of the code that is to be executed by the CUDA card into the cache of the CUDA card, and then execute that on the basically CUDA card or the GPU card. Okay. And finally, then once the calculations have been done, then the results are copied from the GPU memory back to the CPU memory. So once the calculations have completed, the results from the GPU memory are copied back to the CPU memory. So this is how will be the processing flow for CUDA programs. Copy input data from CPU memory to GPU memory first, load GPU program and execute the GPU part of the CUDA program on the CUDA card or GPU card, and while doing that the data are cached on the device memory. Okay, and then finally copy the results from the device memory, that is GPU memory, to the CPU memory. Okay. Getting this, how is the flow of execution for the CUDA program? This is how it will be executed basically. See, I am taking little bit of theory concepts also. So this knowledge will be helpful for you for the theory part also, and because you don't know anything about CUDA. So I am also explaining little theory part so that it helps you for the theory part also, and also the practical part. Okay. So getting what is how the communication happens between the host and the device for executing the CUDA program. Okay. So you have host memory, GPU card and GPU memory in it basically. That is the CUDA card. Okay. Yes, getting how the communication will happen. Okay. Others, Nikhil, Mayuri, are you getting it? Basic concepts of CUDA. Okay. Now we see at the actual program how is basically written on the CUDA card. So what is, suppose you have a simple main program which displays hello world. Okay. So how do we execute it? We go into the terminal and type nvcc program name.cu. So nvcc is the NVIDIA compiler for the CUDA program. Okay. So nvcc hello world name of the program .cu, and finally a dot out. This will display hello world. So NVIDIA compiler nvcc can be used to compile programs with no device code also. So it is not necessary that every CUDA program should have device code or the GPU code present into it. You can write a simple CUDA program without any device code and still can be executed by the NVCC compiler. Okay, but the only thing is it will have no parallelism in it. Okay, that will be the only thing. So if you want parallelism, you need to have device code in the program. Okay, so this is the way you compile the program. NVCC program name.cu, and finally executable file has to be executed, and then you will display the message from the program. Okay. Now if you want to add the device code, how it will look like? So they have added this __ global __ void name of the kernel, my kernel, and argument to it is void, let's say, and no code in it. So this part is the part of the code that gets executed by the CUDA card or the GPU card. Okay. How to invoke that? In the main, you have to say my kernel. This is one block and one thread. We see what are blocks and threads. So how to call the program? My name of the kernel, my kernel, in three opening greater than sign, number of blocks and number of threads, and then again closing angular brackets. So this is how the basically kernel will be called, and then printf hello world. Okay, so this is a simple CUDA program structure for a hello world program, which has device code also present in it. Okay, so this is the way you have to write. So whatever you write between global and void and name of the kernel, that will be executed by the CUDA card. Okay, and how to call that in the main? Name of the kernel, triple angular brackets, number of blocks and number of threads. One we are giving, and then we are printing hello world. Okay. So CUDA C++ keyword underscore underscore global indicates a function that runs on the device, is called from the host code. So it is called from the main, that is from the host code, and it runs on the device, that is the GPU or the CUDA card. So whatever function you write with the global indicates that that function will run on the GPU or the CUDA card. Okay. NVCC separates source code into host and device components. Okay, so NVCC basically separates the source code into what will be executed by the host and what will be executed by the device. Device component example, my kernel processed by the NVIDIA compiler. Host functions example, main processed by the standard host compiler GCC or CL. So the device part will be handled by the NVIDIA compiler, okay, and the host function, that is the main function of the program, will be handled by the host compiler like GCC, okay. So whatever is written after global underscore underscore global will be handled by the device. It runs on the device and it is called from the host code. So if you look at this, underscore underscore global, this my kernel function, though it is not having code at the moment, but if it would have had some code in it, it would have been executed by the device, and in the main that particular function is being called from the host. So the calling the name of the function, number of blocks and number of threads, okay, it is being called from the main. Okay. So the triple angle brackets mark a call from host code to device code. So this triple angular brackets, they basically show that from the host, the device code is being executed, called basically to execute from the device basically. This is also called a kernel launch. So this is also called as a kernel launch. So this function given in global is also called as a kernel function, okay, which will be executed on the device, that is GPU, that is the CUDA card. Okay. So that is all that is required to execute a function on the GPU. So this is how you can execute a function on the CUDA card or the GPU. Okay. So you have this hello world with device code. So main, the kernel function is called using triple angular bracket, number of blocks, number of threads, and calling that function that will be executed on the CUDA card. And then the printing hello world, which will be executed on the host CPU. Okay. And how to compile the program? NVCC program name.cu and then a.out, that will display hello world. Currently my kernel is not doing any work in its function. It is just for the sample program. Okay, but it will be the one that will be executed on the CUDA card or the GPU card. Okay. So are you getting the basic structure of a CUDA program? It will have a kernel which is identified by underscore global, again underscore space, name of the basically kernel function, return type and arguments. Okay, and how it is called? Name of the kernel function, 3 angular brackets, number of blocks, number of threads, 3 closing angular brackets, and then round brackets. Okay, we'll discuss further what is all of that. Are you getting at least the structure of it? How a basic simple CUDA hello world program can be written? So this will be useful for your theory part also and practical also. Okay. As I told you, the 6th unit almost 40% part is the practical part. Okay. So there it will be useful to you. 40 to 50% of the unit 6 is the practical part of CUDA. Okay. Getting this? Yes. Yes, others also. Are you getting it? Nikhil, Mayuri, and others. Okay. So basically, what is the use of GPU computing is about massive parallelism. Okay. So we see an example that exploits parallelism so that you get faster results. So we see by adding 2 integers and then build up to vector addition. So we see a program for adding 2 integers and then we change it for vector addition. In your basically practical part you have vector addition. So first we'll look at simple addition, then we'll go into vector addition. Okay. So a simple kernel to add 2 integers. So you have underscore global underscore void, name of the function, let's kernel function is add in this case. It is having 3 integer arguments. Okay. And then value at C equal to value at A plus value at B. So simple addition of 2 integers and result in the third integer. Now as before, underscore global is a CUDA C++ keyword, meaning add will execute on the device. Add will be called from the host using the angular brackets and number of blocks and threads. The add will be called from the host, that is from the main, and add will be executed on the CUDA card or the GPU card, that is it will be executed on the device. Okay. Now since add runs on the device, A, B and C must point to device memory. So A, B and C should basically point to device memory, since basically add is executing on the CUDA card or the device. So A, B, C variable should also be stored in the device memory or the CUDA card memory. Okay. So we need to allocate memory on the GPU basically. So what we need to do is that we need to allocate memory not in the CPU memory but in the GPU memory for device related code execution. For whatever is related to host related execution can be done in the normal computer memory, but whatever is to be executed on the device, we need to basically allocate memory on the GPU, in the GPU memory. Okay. Now host and device memory are separate entities. Device pointers point to GPU memory, okay, and host pointers point to CPU memory. So these device pointers, they may be passed to or from host code, may not be dereferenced in the host code. So what you can do is that the GPU device pointers can be passed from host to CPU to GPU or from GPU to host. Okay. Same thing for host pointers which point to CPU memory may be passed to or from device code. So host memory also can be passed to device or received from device. So there are simple CUDA API for handling device memory. You have CUDA malloc, similar to malloc that we have in C++. CUDA free, similar to free that we have in C++. And CUDA mem copy, similar to memory copy that we have in C++. So you have CUDA malloc, CUDA free, CUDA memory copy. CUDA malloc is to allocate memory in the device memory or the GPU memory. Okay. CUDA free is to free the memory. CUDA memory copy is to copy from host to GPU or from GPU to host. Okay. Getting this concept? I know it's new for you. I'll be sharing with you the PPT for the revision purpose. Okay. But before we look at the program, it is very necessary that you know all these things because they are being used in the CUDA program. So all this CUDA malloc, CUDA free, CUDA mem copy will be used in the CUDA program. So these are some of the APIs which are used to handle the device memory, that is the GPU or the CUDA card memory. Okay. Getting the names of the APIs, we see how they are used basically. But getting what are the APIs used to handle the device memory. Okay. Yes, getting this. See, all this is required for theory also. So I'm using the PPTs for both the purpose, for practical also and theory part also. Okay. I'll be sharing with you the PDF also, just like for first 5 units. I'd share the book with you. For the 6th unit also there is a book provided by the syllabus. I'll be sharing with you the PDF for that. So that is also a good reference for your study purpose. Okay. Yes, getting this part? Yes, others? Prasanna, getting this? Mayuri and others also. Nikhil, getting this? Okay. So this was our add function, that is a kernel function which will execute on the device, underscore underscore global underscore underscore void add with 3 arguments, integer pointers, and the C equal to value at C equal to value of A plus value at B. Okay. Now let's look at the main. Okay, so main will be executed on the host, whereas the kernel will be executed on the device. Okay, so yeah, there are three variables A, B, C, which are basically the host copies of A, B, C, and you are having three integer pointers which are device copies of A, B, C. Okay, so int size of int has been taken in the size. Okay, allocate space for device copies of ABC. So now we'll have to create space in the device memory, that is the GPU memory. So that is done using CUDA malloc void pointer star star ampersand d underscore a. So basically d underscore a will be allocated in the device memory, that is the GPU memory. Similarly, d underscore b will be allocated in the device memory, and d underscore c space will also be allocated in the device memory. Okay, using CUDA malloc. Then basically two variables are initialized in the main, a equal to 2 and b equal to 7. So CUDA malloc what will do is that allocate space for device copies of A, B and C. So in the device, that is the card, GC CUDA card, these three variables will be allocated memory, D underscore A, D underscore B and D underscore C. Okay, and two variables are allocated memory in the host memory, A, B and C. Two A and B will be initialized, C will not be initialized. Okay. Then copy inputs to device. Okay, so from the host to the device, the values are passed. So CUDA mem copy, A value will be copied to D underscore A, and it is having CUDA mem copy host to device. From the computer CPU memory to the CUDA card device memory, A value will be copied from A to D underscore A, and B value will be copied from B to D underscore B. Okay, CUDA mem copy host to device. Okay, from B the value will be copied to D underscore B. Okay, so CUDA mem copy host to device. Okay, then basically launch add kernel on GPU. So add name of the function add, number of blocks 1, number of threads 1. There are three arguments passed to it, D underscore A, D underscore B and D underscore C. Okay. So like you had seen, the kernel has three arguments, int A, B and C. So they are passed as D underscore A because that they are present in the CUDA. We have allocated variables for that, D underscore A, D underscore B and D underscore C. Now once the calculation is done in this particular add function, C will contain the result, that is D underscore C has been passed here. So D underscore C will contain the result in the device memory. Okay. So what will happen is that result has to be copied back to the C variable in the main. So again we are using copy result back to host, CUDA mem copy ampersand C, D underscore C. So D underscore C value will be copied from the device memory to the variable C in the host memory. So the direction is what? CUDA mem copy device to host. So now we are copying from the CUDA card to the CPU memory. Okay. So this is the memory copy from D underscore C, that is device variable, to the variable in the host PC. Okay. So that will copy the result from the device memory to the host memory, that is the CPU memory. Okay. And finally then we are freeing up the CUDA card related variables. D underscore A, D underscore B and D underscore C are cleared using CUDA free. So this is a complete program for addition of two integers using basically CUDA card or GPU card. Okay. Getting this program? Yes? So basically the kernel part of the program will execute on the device. Then we are copying from the host to the device memory variables. Then we are doing calculation on the device, that is the CUDA card. And then we are copying the result from the device to the host memory. Okay? Getting this? So it's a simple addition program that will be executed on the CUDA card. So this is part of your theory also. You have to write simple program for addition. So we have covered that part also in this session. Okay. In the theory also we require this concept. Yes, clear with this? Yes, Vaibhavi, Nikhil, Yash, Prasanna and others. So simple program they have given initially, simple addition of two numbers. Okay, initially we started with hello world. We saw simple hello world program. Now we have done addition of two numbers using CUDA programming. Okay. So only thing we have to do when we are executing is that we have to save the program as .cu file on the machine that has a CUDA card attached to it, and in the terminal we have to type nvcc program name .cu and finally execute it using a.out. These are the steps for executing the program. If possible, in the next week I'll show you online using a CUDA card machine. Not today, I'll not show you the output today. I'm just going to explain you the programming concepts associated with CUDA. Okay. The next week maybe I'll show you a demo if possible. Okay. So initially understand the logic. The running part is only nvcc program name.cu and a.out. That is all you have to do in running the program. What is important, the how to write the program. That is what we are discussing in this session. Okay. What is the logic of the program? What are the concepts of the program? How to write the program? That is what we are discussing in this session. Okay. Now we see the concept of blocks in the CUDA program. Okay. So GPU computing is about massive parallelism. So how to run a code in parallel on the device? So normally we had said add 1 comma 1. So it was executing only once in on the GPU card. But if you say add n comma 1 or add 1 comma n. So if you say add n comma 1, then n times in parallel this add will be executed on the GPU card. So add n comma 1 will execute n times this kernel function add parallelly. Okay, or you could have also said add 1 comma n. Both ways can be used. Now when you say add n comma 1, n blocks will be executed parallelly on the CUDA card. Okay. So they have given an example. With add running in parallel, we do vector addition. So we are going to use add in parallel for doing vector addition. Okay. So terminology, each parallel invocation of add is referred to as a block. So you can have parallel blocks executing, or within a block you can have threads executing. So in this example we are going to take the example of blocks. The set of blocks is referred to as a grid. So blocks are in grid and threads are within blocks. Okay. Each invocation can refer to its block index using block id.x. So each block can be handled by using block idx.x. So when you pass A, B and C to the add, you can have C block ID X dot X and A of block ID X dot X plus B of block ID X dot X. So since parallelly the blocks are being executed, by using block ID X dot X to index into the array, each block handles a different index. So for one block, you will have one C A plus B addition done. For another block, you will have another A plus B addition done and stored in the C array. Okay. So each A plus B addition will be done per block. Okay. So like block 0 doing C of 0 equal to A of 0 plus B of 0. Block 1 doing C of 1 equal to A of 1 plus B of 1 and so on. Okay, each block doing one element addition in parallel. So on the device, each block can execute in parallel basically. Okay, so how is the function written for that? Vector addition underscore underscore global underscore underscore void add three parameters A, B and C. Now they are arrays basically, integer arrays. So C of block ID X dot X, similarly A of ID dot X and B of ID dot X. Okay. So how it will execute? Block 0 will execute with C of 0 equal to A of 0 plus B of 0. Block 1 will have one index into it, 2 will have 2 index and so on. Okay. Getting this concept, first of all, how to execute parallelly, we'll see how to call that and all those things. But understand that vector addition can be done by parallelly executing the blocks. So grid contains blocks and each block contains threads. Okay. So in our program they have used threads instead of blocks. We'll see what are threads also. So you can either use blocks in parallel or within the same block you can use threads in parallel. Okay. So you should know both. They are part of the syllabus. Block also parallelism and thread parallelism. Okay. Yes, getting this. So in the angular brackets, the first parameter is number of blocks and the second parameter is number of threads. So what we have given n comma 1. We could have given 1 comma n also, one block and multiple threads. Or we can give multiple blocks, per block one thread. Okay. Yes, getting this. We'll go in details further. We have not completed the program. Okay. Okay. So this is our add kernel function, which is done for C equal to C of array equal to A of array element plus B of array element. Okay, then let's look at the main. So let's say they have defined n as 512. So you can easily imagine 512 blocks will be parallelly executing on the GPU card. So obviously speed benefit you will get. 512 parallel additions will be done on the vector. Okay. Now again they have declared three variables A, B, C. Then device copies of A, B, C have been taken. Okay. Then CUDA malloc D comma underscore A, D underscore B and D underscore C, and size will be n into size of int because it's a vector now. A is all D underscore A is also a vector, D underscore B is also a vector and D underscore C is also a vector. Okay. Then they have allocated A, B and C also as vectors in the CPU memory. Okay. And they are initialized using random values. Okay, so A has been initialized with random n numbers, B has been initialized with random n numbers, and C will store the addition of A and B. Okay, then what we are doing, again same thing, like we copied a integer A into D underscore A in the earlier example. Here the entire vector A, array A, is copied into D underscore A vector. Again B vector from the host memory is copied into D underscore B device memory vector value. So again it is memory copy from host to device. So CUDA memory copy from host to device has been done using these two statements. Okay. Then launch has been done, launch kernel function add on GPU with n blocks. So n is the number of blocks and 1 is the number of threads. Okay. So n blocks and per block 1 thread, and has been passed with D underscore A, D underscore B and D underscore C. So because of this call, what will happen is that this add will execute on the device. The kernel function add will execute on the device. Okay. So once it has executed on the device, in the D underscore C will get the result in the device memory. So from the device memory, D underscore C is copied into C vector in the host memory. So CUDA memory copy device to host. So CUDA mem copy is basically copying from D underscore C basically vector in the device memory to the C vector in the host memory. Okay. And finally then we are cleaning up free A, B and C and CUDA free D underscore A, CUDA free D underscore B and CUDA free D underscore C. Okay. So we are clearing up the CUDA memory and the host memory. So this will do vector addition of D underscore B and D underscore A and store the result in D underscore C. Is getting the program? Understood how to write a kernel, how to invoke a kernel, how to do CUDA malloc, how to do CUDA free, how to do CUDA mem copy. All these are new things to you. That's why I'm discussing about that. So these are all the features that are required for CUDA programming, simple CUDA. We have to do vector addition. I think that is the assignment for you in the practical also that we discussed now. Okay. And that is also part of the theory 6th unit. 50% of the 6th unit is containing all these concepts. Okay. Getting this? Yes. And so once you write this CU program, .cu program, go into the terminal, execute it by nvcc program name .cu and finally a.out. Okay. Yes, clear with this? Prasanna, Nikhil, others, Kiran, Samyak. Mayuri, yes, clear with this? So this is how parallel programming can be written. Yes, number of blocks will be 512, yes. Clear with that, Prasanna? Okay. So what we discussed, difference between host and device. Host is the CPU, device is the GPU. Using underscore underscore global and again underscore underscore to declare a function as device code, the kernel function, which executes on the device and called from the host. How it is called? name of the kernel function, triple angular brackets, number of blocks, comma number of threads, closing angular, triple angular brackets, and then argument if there is any passed to the basically function. Okay, so like we had seen here, add was the kernel function, triple angular bracket, number of blocks, number of threads, and arguments to the kernel function. Okay. Then passing parameters from host code to device function. That we did using CUDA memory copy. CUDA mem CPY copy. Okay. That way we copied from host to device. Okay. Then basic device memory management, CUDA malloc, CUDA mem copy, CUDA free. Okay. Then launching parallel kernels, launch n copies of add with add in angular brackets n comma 1 and use block id x dot x to access block index. Okay. So this is how we execute the multiple block code on the CUDA card. Now in the next session, maybe during the theory part also, we'll discuss how to have parallel threads. And then maybe I'll show you the program that we are implemented, the same vector addition, just instead of multiple blocks, we'll have multiple threads in it. Okay? Clear with, you can use this code also for your practical, the fourth practical. This code will also do. It is not mentioned that whether you want multiple blocks or multiple threads. It has to be executed in parallelly. Okay? So you may use this code or maybe whatever I'm going to share in the next week, that code. Okay? Both are logically almost similar. Just in one code there are multiple blocks and one thread. In the another code there are one thread and one block and multiple threads. Okay? So you can use any one of the version you want. Okay? Okay, give me a couple of minutes. I'll just take your attendance.